Welcome back. We're now on 9.2, relating pressure, volume, amount, temperature, the ideal gas law. So here we're going to identify the mathematical relationships between the various properties of gases and use the ideal gas law and related gas laws to compute the values of various gas properties under specified conditions. So one thing is just something to keep in mind is when we have some constant pressure and temperature, a gas expands uniformly to fill the container in which it's contained. So you're not going to have some closed container and your gas is just sitting down here. Not going to happen. In reality, you have your container and the gas molecules are just going to be bouncing around everywhere, all over the container, filling it up. So remember, gases take the shape and the volume of their container. So there's a ton of different types of gases. We have our elements, argon, helium, hydrogen, nitrogen, oxygen, just as some examples. We have compounds like carbon dioxide, carbon monoxide, water, ammonia. Everything can become a gas too with the right conditions. Now, all gases have the same dependence on four properties: volume, amount, temperature, and pressure. So here's just some sketches. 1783, we had the first hydrogen-filled balloon flight. And then we see a manned hot air balloon flight in B, and then picture C, a manned hydrogen-filled balloon flight. And just we can see, I guess, apparently the hydrogen balloon, when it landed, the frightened villagers of Gonesse, I don't know if I said that right, destroyed it with pitchforks and knives because they were scared of it. Okay, so we're going to start talking about how some of these properties of gases relate to each other, starting with pressure and temperature. So the pressure of a gas has been found to be directly proportional to its temperature in Kelvin. So one of the first things that I need to stress is that for gases, the temperature needs to be in Kelvin. We cannot do Celsius, we cannot do Fahrenheit, only Kelvin. Kelvin has no negative temperatures associated with it. The lowest temperature is 0 Kelvin, aka absolute zero. So, which makes sense when we're doing these calculations. You'll see later, we can't have a negative pressure. We can't have a negative volume. So we have to say the positives, we have to use Kelvin. So again, pressure is directly proportional to temperature. So we denote that by saying P, and then this little symbol here means directly proportional, or it means is proportional to. So pressure is proportional to temperature. So that tells us as one goes up, the other goes up. If I increase the pressure of a system, the temperature of it goes up. If I increase the temperature, the pressure goes up. And this makes sense because pressure is the amount of times that your gas, for instance, is hitting the sides of its container. If you bring up the temperature, you're making the gas move faster, so it's going to hit the sides of the container more often, giving you higher pressure. So to equate pressure and temperature, if we're looking at just one system, we know they're proportional, but there has to be some type of proportionality constant to see this. So pressure is equal to some constant times T. This constant is, we could also say, is equal to pressure divided by T. So this is a constant though, which means that if I have the same system, everything else is the same, and I increase the pressure or increase the temperature, the other one is going to go up as well. But that ratio of pressure divided by temperature still equals K. So if I had some P1 over T1 equal to K, and I also have a P2 over T2 equal to K, I can set those in equal to each other. So we get a Montan's law or Gay-Lussac's law. I was taught it as Gay-Lussac's law, doesn't really matter. But this is that your initial pressure divided by your initial temperature is equal to your second pressure divided by your second temperature. So as long as you know 3 of these, you can solve for the 4th one. Again, your temperature must be in Kelvin when you do this calculation. So if you're given a temperature in Celsius, you need to convert it to Kelvin. and then do your solving. So here's some visuals showing you some gas that's in a closed system. So one thing to notice here with the Guy-Lussac's law is, I'm going to go back here, constant volume, and that N means number of moles. So the volume in our container is not changing. We aren't taking any gas out. We're not putting any gas in. So if we take this container of some gas and we put it in some cold water, we have a lower pressure. But as we start heating it up, the pressure starts going up. Our gas container can't expand. We're not magically creating more or taking gas out, so the pressure is going to go up accordingly. One thing I also want to stress with this is nowhere are we talking about what type of gas. For these gases, these are called ideal gases, the type of gas doesn't matter. Type of gas does not matter. If you were to look at pressure and temperature on a graph, so you're in the lab and you're measuring pressure as you change your temperature, what you would notice is this steady increase, this linear relationship. So if you remember with the graph, y equals mx plus b. Okay, so the slope of your graph here, this m, is your k. Okay, it's a change, your change in pressure over change in temperature, delta y over delta x, pressure over temperature. Hey, look, that's equal to k from when we were first looking at this equation. So that k then, that constant, is the slope of your graph. And if we were to take this graph and extrapolate, so these are the measurements, the solid line that we took in the lab, and we go, okay, now I have the linear fit for this graph. I got the equation of it. And we can extrapolate this by plugging in 0 for y and 0 for x. What we should find is there's absolute 0. If we were to then change it to a Celsius scale, we would eventually find that our temperature at a pressure of 0 is negative 273 degrees Celsius, which is absolute 0. So let's look at a quick example. And we're talking about a can of hairspray here. So it's used until it's empty, except for the propellant isobutane. And this is true. If you look at pretty much any type of aerosol canister, it has a warning that says store only at temperatures below 120 degrees Fahrenheit. Do not incinerate. And when you think about this, you want to think about why. Okay, so the volume of our cans really can't change, can they? So you start putting it in a fire or you start heating it up, now that pressure, the temperature is going up, and that pressure is going to build up and build up and build up until the can cannot take it anymore and it can burst. And so it can explode, and then isobutane is combustible, so you could make not only the can burst but have a big fire explosion, and that's bad. So the second question, the gas in the can is initially at 24 degrees Celsius and 360 kilopascals, and the can has a volume of 350 milliliters. If it's left in a car that reaches 50 degrees Celsius on a hot day, what is the new pressure in the can? So they gave us some extra information we don't need. They gave us the volume of it. We're going to assume this volume doesn't change, so that's just extra information that's there to confuse us. So we have an initial temperature of 24 degrees Celsius, but we can't do anything with that Celsius until we change it to Kelvin. So we need to go ahead then and add 273 to that. And that gives us 297 Kelvin. And then we have a P1 of 360 kilopascals. One thing here, while temperature has to be in Kelvin, the rest of your units, like your pressure, actually doesn't matter what type of pressure you're using as long as it's the same. So we can go ahead and stick with kilopascals here, and that's just going to be the same units as our answer because they would cancel out. So, and then we have a T2. We were given as 50 degrees Celsius. Again, add 273 to that, and we get 323 Kelvin. So we're going to start with P1 over T1 equals P2 over T2, and we are solving for P2. So to get P2 by itself, we can multiply both sides times T2. So that gives us P1 T2 over T1 is equal to P2. Plug in our numbers and you get 390 kilopascals. And this makes sense, right? Our temperature went up, therefore our pressure needs to go up because they are directly proportional. So next up is volume and temperature. So the volume of a gas is directly proportional to temperature. And again, temperature in Kelvin. So volume is directly proportional to temperature. And this one, we have constant pressure and moles. So this is something like maybe a piston. So you have a container here and you've got a movable piston. Okay, and so that can move up and down, thus changing the volume of our container. So if I have this container and then I go ahead and I move this piston down into the container. So what I've done is I've decreased the volume. And so now what's going to happen is these molecules are going to start moving faster. Well, actually, they're not going to start moving fast. Sorry. We've decreased the volume. Our pressure, though, needs to stay the same. So these molecules now have to start moving slower, which means they have to get colder. So our temperature is going down. This is called Charles's law, or Charles' law. So our volume divided by temperature is equal to K, just like we did before. It's very similar. V1 now over T1 is equal to V2 over T2. So very similar to the last gas law, only this time is volume and temperature instead of pressure. Same type of thing in that you have a linear relationship between the two. For an example, we have a sample of carbon dioxide. We're given a volume at 10 degrees Celsius and 750 torr. What volume will it have at 30 degrees Celsius and 750 torr? So it's telling us our pressure is the same. So we don't even need that information. So that is one way, though, to know, okay, this is Charles's law. So if you have multiple problems and you're not sure which one to use, you could say, oh, pressure is constant, amount of gas is constant. So that means Charles's law. So we have a V1 of 0.300 liters. We have a T1 of 10 degrees Celsius plus 273 is 283 Kelvin. We have a V2 that we don't know. I don't know why they made that into a 3. But we don't know. And a T2 of 30 degrees Celsius plus 273, 303 Kelvin. So before we even start solving for this, we see our temperature went up, which means our volume needs to go up. So we're solving for V2 here. So multiply both sides times T2. V1 T2 over T1 equals V2. Plug and chug, and we get 0.321 liters for our volume. Again, we raised the temperature, so that means our volume needs to go up. Another example, we are looking at a thermometer, and we have this mixture, blah, blah, blah. So we're talking about some volume of the hydrogens. Pressure is the same. We're looking at boiling ammonia, excuse me. We started at 0 degrees Celsius. And we have a new volume. So we have a first volume, 150 cubic centimeters. Then we went down to 131.7 cubic centimeters. And we want to know what the temperature is of the boiling ammonia. So let's start by writing what we know. We have a V1 of 150.0 cubic centimeters. We have a T1 of 0 degrees Celsius plus 273. So this is, I guess we want to be a little bit more exact here since we're given more sig figs. So technically it's plus 273.5. So it's 273.15 Kelvin. And we have a V2 of 131.7 cubic centimeters. In this case, we want T2. So an easier way to solve for this is to use our old friend from like junior high, cross multiplying. So when we cross multiply from V1 over T1 equals V2 over T2, we get V1 T2 equals V2 T1. Divide both sides by V1. We're solving for T2. So we get that T2 is equal to V2 T1 over V1. Plug in all of our numbers and we get 239.8 Kelvin, which makes sense. Our volume went down. Our temperature then should have gone down, right? That 239.8 lower than 273.15. And the last step is to go from Kelvin to Celsius, and you subtract 273.15 and you get negative 33.4 degrees Celsius. And this also demonstrates why we can't use Celsius. If you were to put 0 degrees Celsius in this equation, for one, you'd be trying to divide by 0. You can't do that, it blows up. And even if we could, you wouldn't get that negative number because you can't just make a negative number like that with multiplication and division. All right, next up, volume and pressure. Now, the volume of a gas is inversely proportional to its pressure. So V is proportional to 1 over P. So what that tells us is as one goes up, the other goes down. So at constant temperature and moles of gas. So now temperature and moles are constant. Volume is equal to your proportionality constant divided by P, or K times 1 over P. Or this constant is equal to P times V. So again, as pressure goes up, volume goes down. As volume goes up, pressure goes down. So this can simplify down to Boyle's law of P1 V1 equals P2 V2. So just to kind of show this, if you were to graph pressure versus volume itself, you end up getting a parabola in your graph. And you can see a relationship between them, but it's parabolic. It's not very easy to predict or even fit with linear regression. However, if you go ahead and do 1 divided by pressure and plot that versus volume, you get a nice, beautiful straight line that then you can actually get better data off of. So again, they are inversely proportional to each other. An example of Boyle's law is breathing. As you breathe in, you're creating different pressure differences between your lungs and your surroundings, causing air to come in and then be forced out of your lungs. So let's look at example 9.8, looking at this gas, and I copied and pasted the graphs that it's referring to that we just looked at. We're told it has a volume of 15 milliliters at a pressure of 13 psi, and we want the pressure of the gas at a volume of 7.5 milliliters using 3 different ways. The first one is using the PV graph, so that's this one here. So we have a volume of 7.5, so that's about here, and we try to go up, up, up. To me, it looks like about 30-ish psi. So the book estimates 27 psi. And then looking at 1 over P versus V graph. Okay, you get like, so your 1 over pressure, I'm going to say it's 0.04. And that's 1 over psi. So that means now I need to do 1 divided by 0.04 to get it to a pressure. And I get about 25 psi. Of course, technically, the way that it would be best to do it using the line is you get the actual equation of the line, and then you plug in your volume and solve for your y, and then you can do 1 over it. But nonetheless, Now let's go ahead and go to Boyle's law from the information that we're given. We have a V1 equals 15 milliliters. We have a P1 equals 13.0 psi. And we have a V2 of 7.5 milliliters, and we want P2. So we have P1 V1 equals P2 V2. Solve for P2, we're going to divide both sides by V2. So P2 is equal to P1 V1 over V2. Plug in our numbers and we get 26 psi. So the calculation gives us a much more accurate number. Our next law is Avogadro's law, and this looks at volume in moles. So now this one has constant temperature and pressure. Avogadro's law isn't quite as talked about, but it's a very important law nonetheless. So this is why balloons blow up or why we're able to inflate basketballs. Okay, so volume is directly proportional to the amount or moles of a gas. And we say moles by using an N. So N means moles of gas. As the volume goes up, the number of moles goes up, which makes sense. If you're blowing up a balloon, when you're blowing into it, you're putting gas from your lungs, you're blowing air into the balloon. You're putting in moles of a gas, and what happens? The balloon expands. So just like before with our proportional equations, this becomes V1 over N1 equals V2 over N2. Again, this is called Avogadro's law. No example for this guy. Your book doesn't even have one. Just kind of keeps moving on. So all of these discoveries and these equations were all circling the same thing, and that is called the ideal gas law. We can combine all of them, and what we get is PV equals nRT, or as those of us weirdos call it, PivNert. So all these four K's were combined into a new constant that we call R, the ideal gas constant. So with PivNert, P is the pressure in atmospheres, V is the volume in liters, N is the moles of gas, T is the temperature in Kelvin, and R is the ideal gas constant. And R is equal to 0.08206 liter ATM per mole Kelvin. There are other R's for other units, usually of pressure, but this is the main R. And notice again, type of gas doesn't matter. There's nowhere here where the type matters. These are ideal gases. We don't care what type of gas they are. We care about how much of the gas there is, but we don't care about what it is. So it accurately describes the properties of an ideal gas. And there's a lot of assumptions being made, and this is something related to kinetic molecular theory that we will talk about later in the chapter next week. But basically, kinetic molecular theory tells us that every gas molecule does its own thing. They don't interact with each other. And yeah, that's the main gist of it. So let's look at some examples using the ideal gas law. Methane, we're looking at, and we're as an alternative to fuel. So natural gas is another word for methane. I've driven a natural gas car before. It's actually the place I did my research has a car. It's an older Honda, that is a natural gas car. And it's weird. There's pretty much no trunk space because the entire trunk is taken up by the container that you pump the gas in. And there's specialized stations to fill up for them. I'm sure some of you have seen them, and you actually have to watch a little training video to even use it. It's really weird. But nonetheless, 1 gallon of gasoline can be replaced by 655 grams of methane. What is the volume of this much methane at 25 degrees Celsius and 745 torr? So one thing to notice here, and where students tend to get confused with these types of problems with our gas laws, is they get used to the singular gas laws like Boyle's law and Avogadro's law, where we're looking at, just two properties. And the thing you need to notice here also is those laws, we're looking at changing the conditions of the gas. The ideal gas law here, PV equals nRT, we're not changing anything. It's like we're taking a snapshot of the gas at one set of numbers. Okay, so again, we want volume. So we have PV equals nRT. Solve for V, divide both everything by P. So volume is equal to nRT over P. Now we have our R constant. And one thing that we should notice here, though, is we have grams of methane. We can't do that, so we need moles of methane. So we're going to have to get its molar mass and then go from grams to moles using that. So we have down here now 6.55 grams of methane times 1 mole per 16.043 grams gives us 40.8 moles of methane. We were given a temperature in 25 degrees Celsius, so we need to make that Kelvin. And lastly, we were given our pressure in torr, which we need to make that into ATM. There's 1 ATM per 760 torr. And now we have everything we need to go ahead and plug and chug. And when you do that, you see our moles cancel from our R constant, ATMs cancel, Kelvins cancel, and the only unit we're left with is liters. And so we get 1.02 times 10 to the third liters. So it would require 1,020 liters of gaseous methane to replace 1 gallon of gasoline. So this is, like I was saying, with those natural gas cars, it's a huge container in the car for the methane gas. It takes up, like I said, the entire trunk. I think it was a Honda... Oh gosh, what's their normal little sedan car? Not an Accord. Nonetheless, little Honda with no trunk. My friend and I actually had kind of forgotten about that, and we went to go pick up a new grad student from LAX who was coming from India. And we go pick him up, forgetting, like, hey, this student's probably going to have a good amount of luggage since he's moving to the United States from India. And then we had to try to get this kid in the back seat with then his luggage because there was no trunk space. It worked, but we felt really bad. All right. So now we're going to kind of play around a little bit with the ideal gas law. But we're going to start by saying our moles are constant, but we're changing pressure, volume, and temperature. So because of this now, we get the combined gas law. And the combined gas law basically takes the ideal gas law and looks at changing the system or taking all those other individual gas laws and putting them together for everything to change. So it is P1V1 over T1 equals P2V2 over T2. And if you look at this and think about it, when you're going, okay, what if temperature is constant? You get rid of the temperatures, the T's in that, boom, you have Boyle's law. So it actually kind of simplifies down to all those individual gas laws depending on what's constant. So you need to carefully analyze the questions that you're given with gas laws. Are things changing? Then you want to look at either using the combined gas law or one of the other mini gas laws. Is everything just one? Is it just one set of conditions? Then you need the regular ideal gas law. Write down what you're given so you can figure out what you need to find and what you need to use. So let's look at an example using the combined gas law. A typical scuba tank has a volume 13.2 liters and a pressure of 153 atm. If the water temperature is 27 degrees Celsius, how many liters of air will a tank provide to a diver's lungs at 70 feet in the ocean where the pressure is 3.13 atm? So we're going to use, we're just kind of saying 2 represents the lungs and 1 represents the tank. It's not ideal, but it'll work. Or we could just say that P1 equals 153 atm, P2 equals 3.13 atm. Don't even worry about diver versus tank. V1 equals 13.2 liters. We don't know V2. But then we also see temperature changes. So T1, let's see, is 27 degrees Celsius plus 273. Gives us 300 Kelvin. And then one thing that they give us is, oh, this is a person, so their air lung temperature, that's our T2, is 37 degrees Celsius plus 273 is 310 Kelvin. So now we have everything except for V2. So to solve for V2, a lot of my students like to cross multiply. So we just say, okay, now we have P1, V1, T2 is equal to P2, V2, T1. And we're looking for V2, so divide everything by P2, T1. So V2 equals P1, V1, T2 over P2, T1. Plug and chug, and you notice everything cancels except for liters, and you get 667 liters. And there's a scuba diver there. And there's the Great Barrier Reef. Stop killing the reef with climate change and pollution. Okay. So one thing that we should define is standard temperature and pressure, or STP. And at STP, we have 0 degrees Celsius, or 273 Kelvin, and 1 ATM. Some things have changed it to 1 bar, but generally we just use 1 ATM. Don't worry about that. So at STP, that means 0 degrees Celsius, 1 ATM pressure. And at STP, what ends up happening is that 1 mole of any gas can be calculated, and it has a volume of 22.4 liters. So 1 mole of a gas is equal to 22.4 liters at STP. So it's definitely something very handy to use. You can use this as a conversion factor. And here's 3 examples. These balloons each have 1 mole of a gas. So they have a volume of 22.4 liters. We're not talking about the mass of the gas, though. Notice, okay, 4 grams of helium, 17 grams of ammonia, 32 grams of oxygen. These are just 1 mole, or 22.4 liters. Still 1 mole of those gases.